When a program is ready to run as a process, it's loaded into memory and stored in a particular layout that looks roughly like this. Now, I say roughly because different systems might have slight variations on this layout, but I think you'll get the idea. The instructions are stored at the start of the process memory, then the global and static variables, then the heap, and then the stack. Now, the stack goes down from the top of memory to the low addresses, but the heap grows up from the global static area towards the end of the memory. The stack is where the local variables of functions are stored, as well as argument values and various housekeeping data items. The heap is not structured. After all, it's a heap, but it's where you can allocate chunks of memory for data structures. When several processes are in memory, and this is the normal case, they each have this layout. Now, I described a simple memory mapping scheme that involved a base and limit register in a previous video. This was the early approach that was adopted to memory management and protecting one process from accessing another process. Now we use much more sophisticated and much more complex schemes that involve remapping smaller blocks of memory individually. Now, these blocks we call pages, and a page is usually small, for example 4096 bytes, 4096 bytes, in other words 4K, and the remapping works by having a table in the system in the memory that contains an entry for each of these pages, each of these blocks, 4K blocks, and an entry that maps the virtual address of the page used by the process to the physical address in the main memory, or an indication that the page is currently not in the memory but is stored somewhere on mass storage. And this table is called the page table. Now, the kernel of the operating system manages this table and moves pages to and from mass storage as needed. Now, what happens if a program attempts to use memory that the page table has mapped out to mass storage? In that case, the access will cause an interrupt that will transfer control to the kernel. And an interrupt is like a forced function call to the kernel that occurs between two instructions in such a way that the CPU state is saved and can be restored when the kernel restarts the process. In this way, the process has no indication that it was interrupted. When the kernel gains control as a result of the interrupt, it will find the page on the disk, stored in an area of the disk we call the swap area or swap space, and read it into a free part of the main memory. Then it sets up the page table to point to the new physical location in main memory and returns to the process. If the kernel needs to read in a page from disk and discovers that there's no free memory, then it first has to select an existing block, write it out to the swap area to free up an area of memory. If this happens too frequently, the system will become very slow and inefficient. This is because the speed of the disk is way less than the speed of the RAM of the main memory. It takes a long while to position the disk and then read the page into the memory. Now, this virtual memory idea has a number of really neat optimizations that are used in modern systems. A couple that I'll describe are shared memory, and this means where separate processes have pages that are mapped to exactly the same physical memory. And this way the processes can either share read-only data or read-only code, such as library functions. And this saves duplicating that code in other parts of the memory. They share the library function area of memory. Or you can also share writable memory for sharing data and therefore be able to communicate between the processes by storing things in this shared data area. But with this, you have to be very careful not to cause problems by overwriting the other process's data. but it's a very useful optimization just with a simple use of the page table pointing to exactly the same page in both processes. The second one is even neater, and this is called copy on write. And what it means is that when a process forks, and you might remember in an earlier video I talked about the fork and exec sequence for starting a process. When a process forks, it completely makes a complete copy of the memory. But with the page table, we don't need to actually copy any memory at all. All we have to do is set up a new page table pointing to exactly the same physical memory. So basically, both processes then share the physical memory pages. What happens when one process wants to write into some memory and the other one actually is running a different program and doesn't want to write in that memory? Well, very simple. When a write is attempted to one of these shared pages, an interrupt occurs, the kernel gains control, and at that point the kernel makes a writable copy of the block and gives that back to one of these processes by changing the virtual memory table, the page table. So that's a very quick introduction to virtual memory. In this video I covered the memory layout of processes, simple memory mapping, the idea of page tables and paging to manage the memory, and swapping backwards and forwards to mass storage, also shared pages and copy on write.